All right, welcome to the stream, everybody. We're gonna get started in just a few minutes. So, yeah. All right, so I have included the 2012 MCQ practice, the publicly released Physics C Mechanics exam in the description. You guys can go to it if you want to follow along with the questions. The answer key is also published in the description. It's the second link. All right, so we're gonna be going over again, like I said, 2012 MCQ. So I'm gonna start off with number one. If you guys have any questions, make sure to send it in the chat. I'll be looking at it while we work through the problems, so feel free to ask questions. All right, so let's go ahead and get started. So my voice is also up. Okay, so I'm guessing everything's working now. We'll go ahead and get started finally. Alright, so the first question is a ball is struck at time t equals 0 and follows a parabolic path shown in the diagram above. The following graphs show quantities possibly associated with the motion as a function of time t, as that air resistance assume that air resistance is negligible and that positive directions are upward and to the right. So the first question is which graph represents the horizontal component of the velocity of the ball? We know that the only force acting on this object as it follows this path is the force of gravity, so that's going to be directed downward, right, on this ball here, which would mean the only component of velocity that's going to be affected is the vertical component, which is going to have some effect. But the horizontal component is always going to stay constant. So if we launched it with some certain velocity at a theta from the horizontal, this component of the velocity will always stay constant. So looking at our options, A shows that the velocity was increasing and decreasing. That would imply there's acceleration in that direction. That's clearly not true, so it cannot be A. B also says that the slope is non-zero, right? A is non-zero, which is not true. Same thing with C. Same thing with D, because these all have some sort of slope, so it has to be E because that's the only one with a slope of 0, which would imply no acceleration, and that makes sense, again, because force of gravity is directed completely downward. So for one, it's going to be E. All right, number 2 says, which of the graphs could possibly represent the horizontal velocity of the ball? So the important thing to note is that the force of gravity is constant as it applies it throughout the path it follows. So the vertical component of the velocity, right, if I were to take its slope, it is going to have to stay constant, which means here I have a differing acceleration, right? One acceleration here, and after some time the acceleration changes. That makes no sense because the slopes here, for some reason, is positive and negative here, which would imply that the acceleration has changed. That's not possible. For B, same thing, it's not possible. And E implies that the acceleration was 0. And in this case, acceleration is supposed to be equal to G, so cannot be E. So we're going to have a constant slope. Now, so we're narrowed it down to C and D, and to pick the correct option, if you read this, it says, assume that the positive direction is upward, right? Which would imply that because our initial velocity was upward, right? We first went up and then we came down. We have to start at a positive y-intercept. So it cannot be C because this says that at time t equals 0, we started off going down. That doesn't make any sense. We started off going up. So it has to be D, and then our y component of the velocity constantly goes down at a constant slope, right? The slope here is going to be, again, G. So the answer to this, number 2, is going to be D. I'll get the next question set up real quick. All right. So number 3 says an object with an initial velocity v naught, as shown above, slides up and then down a long frictionless inclined plane. Which of the following is true of the object as it moves? The first option said is constant acceleration while moving up the plane and a greater acceleration while moving down the plane. So again, this is, you just have to draw it out and look at the forces acting on the object. The only force that acts on the object is going to be the force of gravity, which is going to be directed downward, but a component of it is going to be directed in the direction of the plane, which is going to be mg sine theta. And if you think about it, the quantities of mg sine theta as this object moves up the plane, m stays constant, g stays constant, the theta in here also stays constant, which would mean the acceleration is constant. So for A to claim that the acceleration is greater, that cannot be possible, because even as we're going down, this is still going to stay the same. B says it has constant acceleration while moving up the plane and a smaller acceleration when moving down the plane. Again, same reasoning, not true. C says that it moves with a constant velocity both up and down the plane. This says constant velocity, not acceleration. That's the key word. Velocity does decrease as it goes. I mean, depends on how you define it. The speed decreases initially as we go up. So we don't go at a constant velocity. This object eventually slows down to 0 at the top or somewhere near the top. D says it has the same acceleration as it moves up and down the plane. I like that one, so it's going to be D. We'll just read E. It has a continually varying acceleration as it moves up and down the plane. That's not true. I mean, these are constant. This is a constant acceleration, right? This is a constant force, right? Dividing by m tells us that this is the acceleration. This is constant. Okay. All right. All right, I'm getting the next question set up. Just a minute. Okay, here's number 4. Two blocks of masses M1 and M2 are connected by a massless string that passes over a wheel of mass M, as shown above. The string does not slip on the wheel and exerts tensions T1 and T2 on the blocks. When the wheel is released from rest in the positions shown, it undergoes an angular acceleration and rotates clockwise. Which of the following statements about T1 and T2 is correct? Okay, so because this is a massless pulley, because this is not a massless pulley, we need to realize that the tensions on one side of the pulley is not going to be same. So we got to realize that fact, because it could be same, but we just know that it's not necessary for it to be the same, right? If it was massless, we know the tension is the same on both sides. Okay, so because this is the case, if I were to draw a free body diagram, basically they're asking us which of the following statements is correct. One says T1 is equal to T2 because the wheel has mass. I think the best way to work this out is just first to draw out a free body diagram of M1, which feels a M1G force pulling down and an upward force of the tension force, T1. Now, because we're on the same side of the rope, right, that same tension force is going to be pulling down on the pulley at its tangent to the pulley. T1, it's going to be pulling down on it, right? It's kind of like Newton's third law, but not necessarily. It's like T1 is pulling up on this, which would mean we should be the T1 that's also pulling down on the pulley. Similarly, on the other side, you have M2 with the force of gravity pulling down on it and the tension force T2 pulling upwards. Here, same deal. The T2 force is going to be the tension force is going to be pulling on the mass 2 block, and that same force is going to be pulling down on the pulley. The reason they're the same again is because we're on the same side of the pulley. So if you think about this, they tell us that it undergoes angular acceleration clockwise, so it travels this way. So if you think about the net torque that's acting on the object, you know that's one that's going to be, so if we just think about the radial distance r, right? Don't even think about this. You can just think of, okay, this is the tension 1 is going to create a counterclockwise torque. So that's going to be T1r, that's going to be clockwise. And T2R, this is going to create a counterclockwise. This is going to create a clockwise torque. This is going to create a counter. So we have this one creating a counterclockwise torque, and this one's going to be creating a clockwise torque. Well, what does that mean? That has to mean, because they're acting at the same lever arm, that would have to mean that T2 is greater than, right? So if we look at the options, T1 equals T2 because the wheel has mass. I don't know why that reasoning even makes sense. T1 equals T2 because both blocks have the same acceleration. I mean, again, they literally, that's true, but I don't know how you can prove that. T1 is greater than T2, nope. T1 is greater than T2, no. T2 is greater than T1 because an unbalanced clockwise torque is needed to accelerate the wheel clockwise. Boom. Exact reasoning that I was showing you. So number 4 is going to be E. All right, number 5. 3 objects are located on the x-axis as shown above. The center of mass of the object is at x equals. All you have to do is write down the center of mass equation, which is the sum of each mass times its position from whatever origin you're looking at over the total mass that we're looking at the system for. So each mass we can think of, so here we have 3, the mass of 3 at a distance 0, plus 5 times 3 plus 2 times 5. Okay. Divided by the total mass in the system, 3 plus 5 plus 2. That's going to be equal to, this turns into 0. 5 times 3 is 15. 15 plus 10 is 25 over 3 plus 5 is 8. 8 plus 2 is 10. So that gives us 2.5 meters. That's where the center of mass of the system is, and that's D. Okay, so number 6 says, which of the following is equivalent to the unit of momentum? If we know momentum is equal to m multiplied by v, which is equal to, which in dimensions is kilograms times meters per second, which would imply that, so if we look at joules, joules is force times distance, or newtons times meters. And newtons is the same thing as saying kilograms meters per second squared, because it's mass times acceleration. This is a unit for acceleration. Multiplied by mass would give us kilograms meters cubed over second squared. That's not joules. If we look at newtons, newtons again is kilograms meters per second squared. That's not kilograms meters per second. If we look at joule second, we take Newton meter times seconds. Again, that's kilogram meters per second squared times meters times seconds. We get kilograms meters squared over seconds. Again, that's not it, because it doesn't match with this. This is the momentum's units. Newton times seconds is kilograms meters per second squared. Multiplied by seconds gives us kilograms meters per second. So there it is. That's the correct unit. It's D. If you wanted, you could have done this simple way and just said that delta P is equal to impulse, which is equal to force, average force applied across a certain time. And that would also let you know that this is just newtons times seconds. All right, number 7 says 2 objects are dropped from rest from the same height. Object A falls through a distance dA during time t, and object B falls through a distance dB during time 2t. If air resistance is negligible, what is the relationship between dA and dB? For this one, I think it's simplest to use kinematics equations. So you're just taking delta x equals VIT plus 1/2 AT squared. That's the easiest equations to look at. And they say that we're dropping it from rest. So this equation just becomes, this part goes to 0 because our initial velocity is 0. Because VI is 0, so that part cancels out. And we had 1/2 AT squared. So if we just said dA, right? They say that the object falls through a distance dA if we let it pass through a time t, right? That's what they tell us here. For object B, if we let it pass through a time 2t, then it passes through a distance of dB. So if I just plug in 2t here, that gives us 1/2 a 4t squared is equal to dB. So all we have to do to figure out the relationship between dA and dB, we can just take dA divided by dB. That should be equal to, well, we just plug it in, 1/2 AT squared. I'm just rewriting this here, right? Divided by 1/2 a 4t squared. This would tell us that the 1/2s cancel, the a's cancel, the t squareds cancel, and you get 1/4, which would mean that dA is equal to 1/4 of dB. So then you get A. I mean, that kind of makes sense because the object fell through a distance dA in time t, and if you let it fall through of 2t, it's definitely going to fall a larger distance. Then because it's accelerating, you have the 4 there rather than just a linear difference of just 2. Okay, number 8. The maximum mass that can be hung vertically from a string without breaking the string is 10 kilograms. A length of this string that is 2 meters long is used to rotate a 0.5 kilogram object in a circle on a frictionless table with the string horizontal. The maximum speed that the mass can attain under these conditions without the string breaking is most nearly. For this one, you just have to think about centripetal motion. right? So you have the object moving across in a circle, but it is moving vertically, right? They tell us that it's moving vertically. That's a terrible circle. I'll redraw that. All right, that's even worse, but it's okay. So the maximum mass that can be hung, so this is the tension force that's acting on the object. What you got to realize is that because this is spinning vertically, the maximum tension that you can attain is always at the bottom. The reason is because if the object was at the bottom, right, not only would you be facing a mg force downwards, if you think about it, you'd force force of gravity downwards. You'd also face a tension force upward, right? And if you write your equations down, you get T minus mg is equal to the net force that acts on the object to provide the centripetal acceleration, which we can say AC. This is just Newton's second law. Net force is equal to ma. And this is an A. This is the centripetal acceleration. And you look at it, T is equal to mac plus mg. So at the bottom, you have the addition of these two, right? So you know this is where it's going to have the maximum tension force that it can sustain. At the top, if you write your equations down again, you have the tension force. You have mg pointing downwards, but the tension's also pointing downwards, which means mg is aiding you in the effort to create the centripetal acceleration. So you can say T plus mg is equal to mac, and so T is equal to mac minus mg. So here you don't have as much of the work being done by the tension force from the string, so it can still you know, this is where it can attain its maximum breaking point before the string snaps. So now that we figured this out, it's asking us under what conditions. So we're figuring out Vmax. That's the end goal. Now that we figured out it's going to happen at the bottom, they tell us initially that the maximum mass it can hang vertically from a string without breaking the string is 10 kilograms, which means T max is equal to, well, if a 10 kilogram block is literally sitting on it, mg is going to pull down and T is going to be pulling up. If a 10 kilogram block is what's sitting on it, we have 10 kilograms of mass that is going to supply times gravity. And on the MCQ of the Physics C mechanics test, you can approximate gravity to 10, so don't worry about using 9.8. You get 100 newtons. That's the maximum tension force that this can sustain without breaking. So in this case, we can rewrite this equation as tension minus mg is equal to mac, which would imply that tension is 100 newtons minus the object that we're rotating has a mass of 0.5, so we have 0.5 multiplied by 10 is equal to 0.5 times v squared over r, and the r that we're spinning it about is 2. So if I just hit the left side, 100 minus 0.5 times 10, 95 multiplied by 0.5, so this is 0.5 divided by 2, so you get 95 on this side is equal to 0.5 divided by 2 is v squared over 4. 95 times 4 is 380, is equal to v squared. Taking the square root of 380 gives us 19, so which would imply that v is equal to 19.49 meters per second. And the closest answer to that here is 20, so that's D for 20, for number 8. Okay, number 9. An object moving on a horizontal frictionless surface makes a glancing collision with another object initially at rest on the surface. In this case, which of the following is true about momentum and kinetic energy? Because this object collides with another object, and we're on a frictionless surface, we know that there's no net forces acting on the system, which would imply the momentum is conserved. So what can we say about this? Momentum has to be conserved. So you can already eliminate D because that says momentum is not conserved. So it can't be D. Now, you only know kinetic energy is conserved if they tell you, right? There could have been some heat loss or something in the collision, so you don't know for sure if kinetic energy is always conserved. So momentum is always conserved, and kinetic energy may be conserved, right? Okay. Kinetic energy is always conserved, and momentum may be conserved. That's not correct. C says momentum is always conserved and kinetic energy is never conserved. Not necessarily. So you don't know that. Both momentum and kinetic energy are always conserved in this situation. Not true either. So, they tell you. If they don't tell you, you don't know. So it's got to be A, because kinetic energy, you don't know if it's always going to be conserved. Okay, number 10 says a particle of mass m starts from rest at position x equals 0 and time t equals 0. It moves along the positive x-axis under the influence of a single force. Fx equals b times t, where b is a constant. The velocity v of the particle is given by, we know that the force is equal to mass times acceleration, and because force in the x direction they tell us is bt. To figure out acceleration, you just divide by m. Now, the question asks us for velocity. So if you stopped right there and picked A, you would have gotten it wrong, so do not pick it. The next part is taking this and integrating this function. Right? You're going to take, if you multiply by dt on both sides, you get a dt equals bt over m dt. Take the integral of both sides. And we're just taking an indefinite integral, so it's not really a big deal if you do plus here or not. So this is going to give us velocity is equal to, these are constants, so these can come out of the integral. You have b over m. You have the integral of t dt, and so you get b over m. This is just basic power rule. The physics C exam, especially for mechanics, it's not going to ask you crazy hard calculus that you need to know. I mean, it could be shown up for rotational inertia and stuff, but not really a lot in mechanics. So you just do t. 1 plus 1 is 2 over 2. This is just some basic power rule stuff. So the only thing that matches with this is B, I think. Yeah. So again, don't worry too much about calculus. It's not heavily tested. But on the E&M exam, it's definitely harsher with calculus than mechanics is. Okay, number 11 says 3 blocks A, B, and C of masses 1, 2, and 3 kilograms respectively are initially at rest on a frictionless surface as indicated in the figure. What force F has to be applied on block C to accelerate the 3 blocks at 2 meters per second squared? This one, you just draw a big block that has all of these combined technically because we're just pushing on that block. So here you have 1 plus 2 plus 3 is 6 kilograms. So you're just pushing this entire block at 6 kilograms. The entire concept is if this accelerates at 2 meters per second squared, the entire thing has to accelerate at 2 meters per second squared. That's why I'm able to draw this. And then I can just say F equals ma, and the mass I have is 6 times a, 6 times 2, that gives us 12 newtons. So we're going to have to push with 12 newtons of force to accelerate C and all of them at 2 meters per second squared. Okay, so number 12 says an electrical motor provides 0.5 watts of mechanical power. How much time will it take for the motor to lift a 0.1 kilogram mass at a constant speed from the floor to the shelf 2 meters above the floor? So the object is traveling from here to here. We'll say that's 2 meters of distance as we go from here to here, which would mean, right, because gravity is going to be pulling down on you and you're applying at a constant speed, the only addition of energy that you put into the system, to the block, is the change in its gravitational potential energy, which is going to be mgh, which is mass times gravity times height. We push it up 2, so that gives us 1 times 2 is 2 joules. You add 2 joules, right? So we put in 2 joules into the system in gravitational potential energy as we pull it up. So how long does it take? We know that power is equal to work over time, or work over time, right? The amount of work we do in a certain amount of time. So we can just take 2 joules, we apply 2 joules of amount of work we do in a certain time, which is, we don't know what we're solving for, and that must be equal to 0.5 watts. If I divide and multiply by 2 on the other side, we get 0.5 times 2. Divide, we get t is equal to, dividing by 0.5 on both sides. That gives us t is equal to 4 seconds. So we take 4 seconds for the motor to lift this up and give it 2 joules of energy. And again, that is only if we're moving it at constant speed. If we do put in some energy and this thing has some velocity at the edge, then we have added more than just 2 joules. We have added more to the system. So, but in this case, it's just going to be E. Okay, number 13. A block slides down from rest with negligible friction down the track above, descending a vertical height of 5 meters to point P at the bottom. It then slides on a horizontal surface. The coefficient of friction between the block and the horizontal surface is 0.2. How far does the block slide on the horizontal surface before it comes to rest? So this is just energy conservation. As this block comes down all the way here, all of its potential energy, gravitational potential energy, is converted to kinetic energy. So we can say mgh is equal to 1/2 mv squared. Right? All of the kinetic potential energy initially has been converted to this. There is no loss in friction because they tell us that mu is equal to 0. So if I just cancel my m's, multiply by 2, we get that v is equal to the square root of 2gh. That's the velocity that this object will have at point P. Now, we know that mu is equal to 0.2. So, while thinking about that, they were asking how far does the block slide before it comes to rest. You have initial kinetic. So if you think about initial energy, so right after this, right, you have energy, whatever you have initial, minus the work done by the friction force would give us 0 energy in the system. So here initially we had some energy, and that was all in the form of kinetic energy, and that got converted to 0 some distance away, right? So some energy initially, and some of it was taken away by friction, and that led us finally to 0 joules of energy in the end. So initially we had 1/2 m, and then rather than using v, we'll just use this quantity, gh squared, minus the work done by friction. For this, you're going to have to do force times distance, but here the force that's acting on it is friction, so you can do the normal force, right, multiplied by mu naught. That's going to give you the force of friction multiplied by the distance we travel, which we're trying to solve for, is equal to 0. You can simplify further by saying that Fn is equal to mg, because that's the normal force, by mu naught. That gives you the frictional force multiplied by the distance we act on as a work. So if we add it on both sides, we get 1/2, and if I take the square of a square root, it gives me 2gh is equal to mg mu d, canceling the m's, canceling the g's, canceling the 2's. So we get h is equal to mu d, and h over mu is equal to d. So this is the distance that the object travels. So it all just comes down to, okay, what height did I have? 5 meters over mu naught, which was 0.2. And that gives me, what is 5 divided by 0.2? That's 25. So we travel a total distance of 25 meters before coming to rest. This is kind of crazy because this kind of lets you know that literally nothing about the mass even matters. And it doesn't even matter what the gravity is, right? So it's kind of crazy to think about. All right, 14. The graph above shows velocity as a function of time for an object moving along a straight line. For which of the following scenarios of the graph is the acceleration constant and non-zero? So this is a velocity versus time graph. If we take the derivative of velocity, we get acceleration. So if we take the derivative here in the section p to q, we see that acceleration 0 because the slope is 0. So it cannot be PQ. Anything with a PQ in it is wrong. So it cannot be E or C, right? Okay, what about QR? You can see that the tangent lines here are actually changing. So it looks like this, if I were to enlarge it, QR. If you take the derivative of velocity, right, the tangent lines of the thing, right, it changes. I mean, this is kind of terrible, but you can see that the slope constantly changes each time, which would mean the A isn't constant, so cannot be QR. So you're left with just B or D. Now let's look at the next portion. R to S. Do we have a non-zero slope? That's correct. This is not 0, and it's constant across this entire segment. The slope is always constant. Look at this. We have some constant value that is not equal to 0. Same thing with from S to T. It's not equal to 0. It's some value that's not equal to 0. From T to U, though, we go back to acceleration equaling 0. So the sections are RS and ST. They both work. So it's going to be D. All right, number 15. The velocity of a particle moving along the x-axis is given as a function of time by the expression v of t is equal to 3t squared minus 2t plus 4, where v is in meters per second and t is in seconds. What is the acceleration of the particle at time t equals 2 seconds? Again, dv dt, derivative velocity with respect to time is equal to acceleration. So we just take the derivative of v of t, which gives us, with power rule, that 2 comes down. 3 times 2 is 6t. Minus 2 is probably one of the easier questions on the test. At time t equals 2, we just plug it in. 6 times 2. 2 is 12. 12 minus 2 is 10. So the object's going to have 10 meters per second squared of acceleration. Okay, so number 16 and 17 are both part of the same question. An unstretched ideal spring hangs vertically from a fixed support, a 0.5 kilogram object is then attached to the lower end of the spring. So it's like we have something just standing still, and then now we attach some block to it, which is 0.4 kilograms. The object is then pulled down a distance. So now, after attaching it, we stretch it a certain distance. If this was our equilibrium, we stretch it a distance of 0.35 meters from its unstretched position and released. So now it's going to oscillate back and forth. It's going up and down and up and down, right? It's going to go, it's basically going to have an amplitude of 0.35 meters. A graph of the subsequent vertical position y at the lower end of the spring as a function of t is given above, where y equals 0 when the spring is initially unstretched. So here that's this. Right now, as soon as we hang it, we get some stretch, and then we just stretch it. So basically it stretches to this point, right? I don't know if this is right, but we stretch it to some point and then we let it go. So it just goes back and forth. Okay. They're saying which of the following times is the upward velocity of the object the greatest? Well, you just have to look at the slope of this, right? If you just look at the slopes here, so here it's going to be 0, so that times t equals 0, it's going to be 0. 0.25, so here's 0.5. So here we have the greatest velocity, because again, this is at equilibrium, right? That line is equilibrium. That's what it swings back and forth from, right? So there that is. And at 0.25, yes, we do have an upward facing velocity, because this derivative is going to be positive, which would again imply velocities upwards. So I like B a lot. I can automatically reject A. What about at 0.5? It's 0. That's not going to be correct. 0.75. That is a good guess, because this does have the greatest velocity, but it's in the opposite. I mean, I shouldn't say that. It has the greatest speed, but it's in the opposite direction. So this is pointing downwards. We're going farther down. It's like when the thing is trying to go down now. As soon as it reaches equilibrium at 0.25, we're going up. So it can't be D. In 1 second, it's like, again, 0. So the answer to 16 is going to be B. 17 says, what is the spring constant of the spring? So according to our equations, omega, the angular velocity, is equal to square root of k over m. This is also equal to 2 pi f, or 2 pi over t. So solving for this, we get that if we multiply omega is equal to 2 pi t, 2 pi over t. Actually, we don't need to do that. We can just set these two equal to each other. We can say that square root of k over m is equal to 2 pi over t. Squaring both sides gives us k over m is equal to 4 pi squared over t squared. And so when we solve for k, we just have to multiply by m, which tells us that k is equal to 4 pi squared over t squared multiplied by m. So k is equal to pi squared. The period here is, okay, so if we just go from one point to another point, right, we're going down here, going down at this point. The period here, 0.5. Here, that's 1.5. So we have a period of 1 second, right? That's how long it took. So we have 1 squared multiplied by the mass of the object, 0.4 kilograms. They tell us that right here, so 0.4. All of that simplified tells us that k is 4 pi squared times 0.4. That gives us 15.79. That's closest to A. So 17 is going to be A. Okay, 18 says identical net forces act for the same length of time on two different spherical masses. Oh, I didn't crop this right. This is part of the next question, so don't worry about this. Identical net forces act for the same length of time on two different spherical masses. Which of the following best describes the change in linear momentum of the smaller mass compared to that of the larger mass? Change in momentum is equal to impulse, or the force that's acting on it, integral of the force that acts on it. So if you think about this, we know that dp dt is equal to force net F net. So we just multiply, right? This is basically the derivation for how they got impulse, right? So impulse, change in momentum, is equal to the integral of force times time. And the simpler way to look at this, 4 times dt. A simpler way to look at this is just saying the average force multiplied by a certain change in time interval. So because we have the same force that's acting on the object, this is going to be the same, and in the same time frame, the change in momentum is going to be the same for both of these spherical masses. This is a very similar scenario to when two objects collide with one another, right? According to Newton's third law, they both feel a force on each other. They're equal in magnitude but opposite in direction, because the magnitude of the forces, magnitude of the time is the same, right? In a collision, the magnitude of the change in the momentum of the two objects is also going to be the same. So that's basically a concept. That's the entire concept they're testing in this question. So it cannot be smaller, it's not larger, it's equal to. So 18 is going to be C. Okay, number 19 says the uniform thin rod shown above has mass m and length L. The momentum of inertia of the rod about an axis through its center and perpendicular to the rod is 1/12 ml squared. What is the amount of inertia of the rod? What is the moment of inertia of the rod about an axis perpendicular to the rod and passing through point P, which is halfway between the center and the end of the rod? So here you just have to use a parallel axis theorem, which states that if we just shift it a certain distance from the center of mass that we're rotating it about, you just have to do the inertia on the center about its center of mass plus mass of the object times d, the distance that we move it, squared. It's going to be the final inertia of the object. So here, initially across the center, right, you have 1/12 ml squared plus, now we move it a distance here from the center, a distance of L over 4. That's because this entire part is L over 2. So if you take L over 2 minus this L over 4, if you take L over 2 minus L over 4, that gives you L over 4. So we move it a distance. We just change the axis of rotation. We shifted it by a distance of L over 4. So we can just write m times L over 4 squared is equal to I final. Here this just becomes 1/12 ml squared plus ml squared over 16. If we just add 1/12 and 1/16, my calculator, that gives us 7 over 48 ml squared. That's going to be the final moment of inertia of the object if it's rotating about this end. All right, question 20 is saying a certain one-dimensional conservative force is given as a function of x by the expression F equals negative kx cubed, where F is in newtons and x is in meters. A possible potential energy function U for this force is, you know, the potential energy is equal to the integral of force times the distance we travel, but negative, so the change in this, right? because of this, you can just take the integral of, just plug it in, integral of k x cubed dx. Yeah, here it should have been a dx, doesn't really matter. So what happens is you can plot the constants. You have negative k, and just using power rule, you can add 1 to the 3 and divide by 4. So the only one that matches here is c. This is basically just taking the integral, and you make sure that you multiply by the negative. The negative is very important, right? The reason is because f points toward lower potential. So if we do point in the same direction as lower potential, then the negative just indicates we just lost potential energy. That's all. Actually, for this prior question, I actually messed up here. Because I forgot the negative that they gave me. So this should have been, if I take the integral of negative kx cubed dx, and we have a negative here. I forgot this negative. Sorry about that. These negatives become a positive. This is going to be equal to the change in potential energy. And you just get kx to the 4th over 4. So sorry, this is going to be d, not c. I messed it up because I forgot the negative. Okay, number 21. Which of the following is a differential equation that correctly describes Newton's second law for a simple harmonic oscillator of mass m and restoring force constant k? The force that acts in a simple harmonic oscillator is negative kx. So this is equal to ma. So to write a differential equation, all you have to write is just rewrite a as the second derivative of position with respect to time. There it is. And so the only thing that matches is b. So don't get freaked out by the differential part. They ask this a lot in FRQs. All you have to do is just replace the a or the v with just a position, the respective to position. That's all you need to do. You don't have to worry about it. Okay, 22 says, the elliptical orbit of a comet is shown above. Position 1 and 2 are respectively the farthest and the nearest position to the sun. In position 1, the distance from the comet to the sun is 10 times that at position 2. So all they're saying is, if we say the distance here is d, the distance from the sun to this would be 10d, right? It's 10 times that at the distance from sun to position 2. So at position 2, the comet's kinetic energy is, well, if you think about it, the angular momentum is conserved in the situation, right? Which is going to be r cross p, which is going to be equal to L. Well, at 10d, right, we know for a fact that the radius is greatest here, right? I mean, that's pretty obvious. And at 2, the radius is smallest here because they tell us that. We know also that the angular momentum has to be conserved because there are no net external forces acting, or no net external torques acting on the system. So because of that fact, these are vectors, by the way. Given that fact, all we have to do is say, well, because this is conserved, we just have MVR. This is a rewritten way to say this. And at position 1, our M stays constant. We'd have to look at that. The R was the greatest here, which would have to make V the smallest. The reason is because, again, angular momentum is conserved. And at position 2, we have MVR, and here the radius is the smallest, which would make the V the largest. And because kinetic energy is equal to 1/2 mv squared, we know for a fact that at position 1 we have the lowest kinetic energy, and at position 2 we have the highest kinetic energy. So it's not the same, it's not the less, that's its maximum value for the orbit at position 2. All right, question 23 now says, what is the ratio v1 over v2 of the speed of the comet at position 1 to the speed at position 2? Again, you can just say that angular momentum initially must be equal to the angular momentum final. And here, the angular momentum is r cross p, right? And here we also had r cross p. Let's say that here the position is, we'll say that the angular momentum position 1 must be equal to position 2. So at position 1 we had mvr, and at position 2 we had same thing, mvr, right? But to give better subscript, this is v1 r1 is equal to mv2 r2. We can cancel out the masses, and we know that v1, and then the radius at v1 here, and as we previously said, that was 10d, and here this is d. So if we just replace this with 10d and replace this with d, the d's can go away, right? And we get that v1 over v2 is equal to 1 over 10. So the answer to 23 is B. Okay, so let me switch screens. Okay. 24 says, the elliptical orbit of a comet is shown above. Position 1 and 2 are respectively the farthest, blah, blah, blah. So this is 10. I'll just write that again. 10d. And this is d. What is the ratio, F1 over F2, of the force on the comet at position 1 to the force on the position at on the comet at position 2? You just have to take the force of gravity at position 1 and 2. So the force of gravity at position 1 is G. M1, M2, or the mass of the sun, right? You have that. over, and we can just call this m, and the mass of the sun. So we have m and the mass of the sun over r squared. Well, here we have 10d as our r squared over gm over here and m of the sun over d squared here, because the radius is d compared to 10d over here. So the g's can cancel, the m's can cancel, the sun mass of the suns can cancel, and we get 1 over 100 d squared over 1 over d squared. If we were to bring the d on top, you get d squared over 100 d squared, and then these can cancel, and you get 1 over 100. And that should make sense because the force here is definitely larger, so it cannot be CD or E, and it has to be E. I mean, you can cross CD, E off immediately because there's no way that the force can be greater than 1. I mean, the ratio of the forces can't be greater than 1. So it can't be, it has to be A. Okay, a block of mass m is pulled across a rough surface as shown above. The coefficient of friction between the block and the surface is mu k. The force F that pulls a block is exerted at the angle phi shown. Which of the following is an expression for the magnitude of the frictional force on the block if it is moving at a constant speed? We know that the force of friction is equal to the normal force multiplied by mu. Here the normal force is the force that the floor exerts on the block, right? If we have, so if we just draw a free body diagram, I feel a mg force downward and an upward normal force. Now the normal force basically counteracts whatever it gets pushed on itself by. So because we're applying a force in this direction, the only force that the normal force experiences is the difference between mg and the vertical component of this. The reason is because f sine theta, f sine phi, right, that aids, that helps normal force because we are in the direction, so it doesn't have to push up as hard because this is already decreasing mg by a certain amount. So if we just take mg minus f sine phi, that gives us normal force. And to go back to force of friction, that's equal to normal force multiplied by mu. So as you replace this, you get mg minus f sine phi times mu. So the only option that connects with that is E. So 25 is going to be E. Okay, two 4-kilogram blocks hang from a rope that passes over the two frictionless pulleys as shown in the figure above. What is the tension in the horizontal portion of the rope if the blocks are not moving in the rope and the two pulleys are have negligible mass? Again, because these are negligible, the pulleys, the tension across the rope is going to be the same. So if we just look at this 4-kilogram block, there's one of these 4-kilogram blocks, we know that there is a mg force pulling down on it and a tension force pulling up on it. This is all we have to solve for, the tension force, and because this thing is not moving, the system's not moving, we know that mg minus the tension force is equal to ma, and because this is 0, the acceleration, this entire thing here becomes 0. Mg then equals t, which would imply that we have 4 times 10 is equal to t, so that gives us that tension is equal to 40 newtons. So that's going to be D. Alright, 27 said it was a ball of mass 0.2 kilograms. The ball starts from rest and accelerates horizontally and uniformly through a distance of 0.9 meters and leaves the person's hand at 30 meters per second. The average force, horizontal force applied to the ball by the person's hand is, well, we know that the object, after traveling a distance of 0.9 meters, left with a speed. It left with a speed. Sorry about that. It left with a speed of 30 meters per second, which would mean then that the change in kinetic energy is supplied by the force across a distance, because the object leaves the thing with 30 meters per second. We know that's 1/2 delta V, 1/2 Vf squared minus Vi squared, which goes to the force that's applied, which is the average force that's applied across a distance of 0.9. So solving for this, 1/2 mass is 0.2, and we're left with 30 meters. We don't start with any initial velocity. We just have 30 squared is equal to 0.9 is equal to the force average. Plugging this into the calculator, we get this gives us the answer that average force applied is 100 newtons. So the answer is going to be D. Okay, 28 says a railroad car of mass 1,500 kilograms rolls to the right at 40 meters per second and collides with another railroad car of mass 3,000 kilograms rolling to the left at 3 meters per second. The cars stick together. Their speed immediately after the collision is... One sec, my pen is not working. I'll be right back. Okay, never mind, it's working now. So here is the 1,500 kilogram object that's moving to the right at 4 meters per second, and the other one of 3,000 kilogram that's moving to the left at 3 meters per second. So if we regard to the right as positive and the left as a negative, we can just write our conservation of momentum, because again, no external forces. So we can just solve for the collision. So we get 1,500 multiplied by 4 to the right plus initial. This is initial momentum. All of this I'm going to write down as initial momentum. So you have 3,000. And the velocity is going to be -3, because that's the velocity vector is pointing to the left. Again, we regarded that as negative. You could have swapped it, and you could have said that this is negative and this is positive, but it still worked out fine. And so all of that is equal to, well, because they tell us that they stick together, I'm going to move this to the right a little bit. Because they tell us that they stick together, we can say that the total mass both travel with the same speed. So now this just becomes 1,500 plus 3,000. All of this mass together, they move with the final velocity. So if I just divide by this quantity on both sides, we get Vf is equal to gives us this as negative 2/3 meters per second. But again, they're asking for speed, so we only want the absolute value of this, and that's a. Okay, 29 says a meter stick of negligible mass is placed on a fulcrum at the 0.4 meter mark with a 1 kilogram mass hung at the 0 mark. So if I were to draw this and a 0.5 kilogram mass hung at the 1 meter mark, so here we go, we have the fulcrum here. And this is hung at the 0.4 meter mark. And a 1 kilogram mass is hung at the 1 meter mark. 0 meter mark. So here's a 1 kilogram mass hung at a 0 meter mark. So this is 0 meters, 0.4 meters, and a 0.5 kilogram mass is hung at the 1 meter mark. So here's all the way at the end. We have the mass of a 0.5 kilogram block that's hung here at 1 meters. So the magnitude of the net torque on the object. Okay, so to figure out the net torque, let's figure out this. You just have to take R cross F for each of these. So if I just do that, so the R is well, from here to here, from the axis of rotation to the line of action of the force, that's a distance, the radius, that's a lever arm of 0.4 meters times the force that's acting on it. Well, that's 1 times 10, because mg, this is mg, right? Force times radius, so this is force times radius. That's all I did, I just multiplied them. How to get the sign, right? You're gonna have to use your right hand rule. The equation says torque is equal to R cross F, so you point in the direction, so in this case you point in the direction of R, which is this, and the direction of F, so you cross your hands. If I put my hand in the direction of R and cross it, my thumb points out of the page. So if we say that out of the page is positive, we multiply this by a positive 1. That's it. And then we add this object's I'll keep that blank for the sign, but we'll figure out this object's mass is the force that it applies is 0.5 times 10 mg at a distance here to here, 0.6, right? Because this is the 0.4 mark. If we just take 1 minus 0.4, that gives us 0.6. So, and again, do the same thing here. Point in the direction of R and draw the direction of the force. Now point your direction in the direction of R, cross it to F. That tells me that my thumb points into the page, so we can just, and because we defined out of the page is positive and into the page is negative, this is going to have a negative sign. So if we multiply this, we get 0.5 times 10 is 5 times 0.6 is 3. This is negative 3, and here we just get 4. So that gives us 1 Newton meter of torque. So that's going to be A. Now, you didn't even have to do the right hand rule. You could have just said, hey, look, this creates a counterclockwise torque. So I'm going to assign some sign to it. So I'm going to call it positive, and you could have said this, hey, look, this creates a clockwise torque. So that's going to be negative for me. You could have flipped a sign. It doesn't really matter. Just, I personally like the right hand rule the most because you use it a lot in E&M. So 29 is going to be A. Okay, 30 says an object undergoes simple harmonic motion. Simple harmonic motion, very important. I highly recommend that you guys start underlining things in these questions because they are very useful. The simple harmonic motion is going to come in key along the x-axis shown above, where x equals 0 is the object's equilibrium position. Which of the following graphs best shows a relationship between the object's acceleration a and its displacement x from the equilibrium. You know for a fact that if it's going through simple harmonic motion, a has to be directly proportional to x, right? But in this case, we have negative kx, right? If negative kx is directly proportional to this, because force that it acts upon is directly proportional to the displacement we are from the equilibrium. And that's why the force from a spring or something is always negative kx. So if we just divide by mass, right, to get acceleration, some mass, that tells us that the slope, negative k over m, and so because this is x, the slope here has to be negative k over m, which would imply that the slope has to be negative and constant, right? I like A because it's negative and it's constant. B is positive. I don't like that. C says the slope changes for some reason. I don't know why. D says it's not possible, and E says it's not possible. Now, again, right, it's very important that you realize that there has to be a negative here, very much so, because a conservative force acts always away. It always tries to pull it toward equilibrium. So when you're at a high positive x position, the negative acceleration indicates, like over here, the force is going to be pointing toward the left. That's what even gives you the simple harmonic motion. As you're here, the force pulls you back. As you're here, right, when I'm here, the positive acceleration pulls you to the right, which would indicate a conservative force acting on the system. But here it says I have a positive x and I have a positive acceleration. That would imply then, look, if I'm here, then my force also points to the right, which would mean I'll just keep going out and out. There's no simple harmonic motion in that case. So very important that you pick A, because B and the sign is very important. So keep that in mind. Alright, we're almost done. Last 5 problems. So this one says ball 1 is dropped from rest at time t equals 0 from a tower of height h as shown above. At the same instant, ball 2 is launched upward from the ground with an initial speed v0. If air resistance is negligible, at what time t will the two balls pass each other? What I think is the most important is, I'm just going to say that, well, the moment that they pass, or the distance that they pass at, I'll just call this y. This is where this reaches this point. That's also where this thing reaches, and they both meet. So looking at our kinematics equations, delta y is equal to vit plus 1/2 at squared. And if we look at delta y, the position this object undergoes, right, from here to here, final y minus initial y. Our final y is y, and our initial y is h. So we have y minus h. Now this is the first ball. Again, we're doing the first ball here. The top ball. Now this is going to be equal to vit. Now we're dropping it from rest. And this part goes away. This term goes away. We have 1/2 at squared, and rather than a, I'm just going to replace it with g, because that's what really accelerates this system. So let's do the same equation for the second ball now. So if we look at this, when it goes from here to here, right, the change in height, well, we started with 0 and we went to y, so we do final y minus initial y. Final y is just y, initial y is 0, so we can just say y is equal to vit. This does have initial velocity plus 1/2 gt squared. Look, now we have y here and a y here, so I can just replace the y into that, and that tells me vot plus 1/2 gt squared minus h is equal to 1/2 gt squared. And if I subtract 1/2 gt squared from both sides, this part cancels with this, and we get v naught t is equal to h, and t is equal to h over v naught. So the answer to this is going to be C. All right, 32 is one of the harder questions, I think, on the entire MCQ section. So let's go ahead and do this. Suppose the potential energy of a particle constrained to move along the x-axis can be described by the function u of x is equal to 1/2 kx squared minus ax, where both a, k, and a are positive constants, stable equilibrium points about which the particle oscillates are located at. What you gotta realize is that this is a potential energy function as you go across, as you move across the x-axis. And you can only move in the x-axis, so we don't have to worry about y. Now, the crucial thing to realize is that this is a parabola. So if I were to graph u of x against x, right? If you think about the properties of a parabola, right? I think this is one I would memorize for the AP Physics C exam. Is the axis of symmetry is at negative b over 2a, right? That's where a thing like it's where the axis of symmetry occurs on the x-axis. So if I just plug in my b, which is alpha over 2 times a, well, the a here is 1/2 k. And that tells us that negative alpha makes it a positive. We get alpha over k. Now, that's the point where this parabola, I don't know what it looks like. It could be going through the zero axis. I mean, I'm not really sure what it looks like, but I know for a fact that this is where the object will have the lowest potential energy, because these are positive. This is a positive constant. They literally tell you that, which means it's an upward facing parabola. Because of that one reason, you can say that this has to be the point of lowest potential, because it's a parabola and this is it's upward facing. And the other thing to note is that the force that's acting on this object will always point toward lower potentials. If I have an object here, the force will point to the right, because that's where the lowest potential is. It's right here, right? That's what conservative forces do. They always want to point toward lower potential. And if I'm here, it'll want to point toward the left, right? Because this is where it always wants to go. I mean, think about it. If you have an object on a hill, gravity is a conservative force. It always wants to point toward lower potential. It wants to go here where it is the lowest potential. It has the lowest potential there, right? So because force always points toward lower potential, you know for a fact this is where it's going to stay at equilibrium, right? If I let it go here, it's always going to try to go here, right? I mean, it's not a hill because it's on the x-axis. So if you think about it, this is the point where it's alpha over k. If I let go of a particle here, it's going to go here. If I let go of a particle here, it's going to go here. So it's always going to oscillate about some axis. I mean, it depends, but this is where it's going to be, this is where it's going to have its equilibrium point, because once it's here, the force doesn't really do anything. Anywhere else you let it be, it always wants to go here, right? So keep that in mind. So the answer to this is going to be B, because that's the only place where it has static equilibrium. And this is the point that the object oscillates at. Okay, so 33. I think this one's more of a tricky question, in my opinion, because of the wording. So, a ball of mass m falls vertically, hits the floor with speed vi, and rebounds with the speed vf. So, if we have the floor here, it hits the floor with speed vi, and rebounds with the speed vf. What is the magnitude of the impulse exerted on the ball by the floor? Easy, right? You'd be like, all right, bro, change in momentum is equal to what? Force multiplied by, you have to say change in momentum is equal to m times change in v. So now this is m vf minus vi. So I'm just going to plug it in, right? We have vi, they gave it to me. Boom, this is the answer. I'm going to pick B and I'm done, right? But if you do that, you're going to get the question wrong. What you have to realize is that these quantities here, these are vector, these are velocities, but they give you speed, right? That's very important to note. They didn't give you velocity. If they gave you velocity, you could just say that you could say B and be done. But they gave you speeds. So we're going to have to define a coordinate system and solve this. So if we define up to be positive and down to be negative, we can do the same thing, right? This is still correct. We just have m vf, but vf is a vector, right? It has both magnitude and direction. The magnitude of vf is vf because that's what they gave to us. That's the magnitude, right? And the sign attached to it, that's what gives it the vector, right? So because it's pointing up, we're going to give it a positive. Now this is what the vector is equivalent to, right? Now we're going to subtract the vi vector. So the vi vector is, because it's pointing down, right? We give it a negative symbol, or I'll do this order, which is better. You first give it its magnitude because vectors have magnitude and sign. So first the magnitude, but now attach the sign because that's what this equals, right? We just have an equal sign. We got to make them equal, man. So it's the magnitude. We got the magnitude, right? Now we got to give it its direction. It's pointing down, so I'm going to give it the negative symbol. So because we have two negatives here, we get m vf plus vi. So the answer now is actually C. So always be careful, right? Sometimes they give you speed. It's almost easy to just do it quickly and get it over with. Always think about what a vector means, because I think that's the entire trick in this question. If you get the vector wrong, you get the question wrong. Almost everyone picks B and they just get it wrong. All right, 34 and 35, last two problems. A particle moves in a circle in such a way that the x and y coordinates of its motions are given in meters as functions of time t in seconds are x equals 5 cosine 3t, y equals 5 sine of 3t. If you know parametrics or you're in Calc PC, you should be able to realize that this is a circle. If you were to graph it, it looks like this, right? With the radius of 5. The reason, it's just because it's moving in a circle, and as time progresses, the x position, right? As time goes on, the x position gets smaller, and the y position gets larger, reaching its maximum value of 5 here. And similarly, the y position gets 0, and you reach -5. It just goes on and on, right? So it just goes around the circle. That's basically it. So the radius here is going to be C. I think the easiest way is to just use parametrics. I'm not sure of another way that might be simpler, but I think parametrics might be the easiest, because I think all of you guys who are taking physics C should know parametrics. Unless you're an AB, I don't know how that would work. Again, like I said, you could just think about it graphically. So yeah, it's probably the best way to think about it. Which of the following is true of the speed of the particle? Now, this one's a little trickier. You have to realize that this is going in a circle, which would mean it's going in centripetal motion, right? And you know that because this is moving in a centripetal motion, the speed stays constant. It's always the same across each point. All that happens is that the x component some of the x component goes to the y component. It just keeps going back and forth between them, but the speed is always the same. So if you were to take, right, if you can graph this. If you take dx dt squared plus dy dt squared, and if you graph this as a function on your calculator, you can do that. That's not good notation. If we just graph this as a function of time on your calculator, because this is speed, you will always see that, right? This is the derivative. Second, all I'm doing, right? This is probably the easiest way to think about it. I'm just taking the x position squared plus a y position squared, taking the square root. The v x and vy. So I'm taking the velocity in the x position squared plus the velocity in the y position squared, taking the square root. That's all I'm doing. That gives me the speed, right? Pythagorean theorem. So if I graph this, you will see that this always equals 15 meters per second. If you want, you can think of it like this. If I take dx dt, that's going to be equal to 5 negative sine 3t times 3. So that's going to be equal to negative 15. So the maximum value in the x position is going to be, the maximum velocity in the x direction is going to be 15 meters per second. And which would also mean the total speed also has to match the maximum speed in one direction. Because like at this point, you only have the maximum 15 meters per second. All of it has been transferred to x. And as you go down and down, like over here, you only have y positions velocity. So the answer to this is going to be B. So the answer to 34 is C and 35 is B. All right, so we just ended up finishing all of 2012's MCQ for mechanics. If you guys do want me to go over probable FRQs or something, just leave it in the comments below. I'll try to go over them. But thanks for tuning in to today's live stream. Hopefully it was very helpful for you guys. And yeah, that's it. Thank you. Have a good day, everyone. Good luck on your AP exams.